bunch of you absent from class today because you're taking other AP exams and then went home. So since there's so many people missing, and I talked about escape velocity today, I wanted to put together a little bit of a video for you guys to be able to see, those of you that weren't here today. Question number 34 on the practice exam had some stuff about escape velocity, and since we didn't talk about it much in class over the course of the year, I want you guys to have some exposure to it. All right, when we're talking about escape velocity, let's first make it clear what we're talking about. By the way, I'm going to do this in several parts since it's going to take a few minutes, and so I'll have several small files to look at instead of one huge one. All right, so basically when we're talking about escape velocity, what do we mean? Let's take a look at just a little diagram here. As we are leaving Earth, the idea of escape velocity is as follows. Oh, that's nice. All right, let's get this out of the way. Come back to you later. All right, so here's the deal with escape velocity. The idea is that we are at Earth's surface, and we're going to be fired as a ballistic projectile in such a way that as we leave Earth's surface, of course, we're going to slow down. As we move away from Earth's surface, we're going to lose kinetic energy. Okay, we're going to continue to move out here, and the idea is we have a slowing down, a negative change in kinetic energy, as we get a positive change in gravitational potential energy. The idea is that we're going to move all the way out here. We're going to start with such a speed all the way back here that as we get all the way out here and our velocity approaches zero at a distance that approaches infinity, that our gravitational potential energy will also be equal to zero. What? How can that be? How can we have an increase in potential energy that ends up being zero all the way out here? Our typical idea is that, whoop, that's going to be it. All right, hang on here. Our typical idea used to be that potential energy increases, well, it still is. Our idea is that potential energy increases with increasing distance from the Earth, okay? Well, that must mean that if out here we have a zero potential energy, that out here we must have some negative potential energy. All right, well, let's talk about how that works real quick. Our previous idea, let me move this up here. We're just saying that with positive change in R, that is, as we get farther from Earth, we get a positive change in gravitational potential. That's important. That'll be important later when we're integrating, to know that the direction of R and the direction of our change in gravitational potential have the same sign. Okay? So, according to our old paradigm, the one we're used to, we have an idea that here at Earth's surface, right here, the blue planet, we had a gravitational potential energy of zero. And as we move from the surface out to infinity, we went from having zero to a very large positive value for potential energy. That is to say here, as I've got written here, that gravitational potential energy gets positiver as we move away. Now, of course, positiver isn't a real word. Please don't use that anywhere other than my classroom. All right. So now, instead of thinking of it that way, what we're going to do now is we're going to think about it in a new way. All right? And that is that out here, we're going to say that gravitational potential energy is zero, out where R is infinite, okay? Or approaching infinity for those of you that are going to be math conscious. So now, instead of going that way, outward, we're going to come inward from where we have a zero gravitational potential energy, and we're going to move that way so that now over here we have gravitational potential energy that is a big negative value, okay? We're getting work done by gravity if we're moving in this direction, okay? And work done by gravity is going to be the negative of the change in gravitational potential energy. We've already discussed that before in a uniform gravitational field when we're talking about stuff that happens near Earth's surface. We know that the work done by gravity, if it's positive, is going to cause a positive increase in kinetic energy, and since we are in a conservative situation in a gravitational field, then a positive delta K yields a negative delta gravitational U. Okay? So moving from infinity out here, we get negativer in this direction, and we have a large negative, not delta U, but large negative U gravitation. Okay? Now, this, as weird as it seems, is still consistent with what we've talked about before, that gravitational potential energy increases with increasing distance from Earth's center. Okay? That's no different. As we move away, we get a larger gravitational potential. As we move back, we get a smaller one. We've talked before about where zero is makes no difference. It doesn't matter what we call zero, that it's the changes in gravitational potential that are pertinent to our analysis. Okay? I'm going to call that the end of the first video, and we'll go from there for the second one.